Hello, welcome back to another episode of Math with Haas. You're watching Precalculus Season 1, Episode 16. Now, sadly, this is our last video on exponentials and logarithms, unless I make some more example problem videos that are independent to help assist you with some of the assignment problems. Now, what I want to do in this video is simply review what we did. So, a exponential function has the format y equals a b to dx. Alright. And we stipulated that b is going to be greater than 0 and b does not equal 1. Alright. So we stipulated it had to be positive because when you have a negative value to an exponent, like negative 2 to dx, that is going to create some problems because you can think of it as negative 1 to dx times 2 to dx. And this quantity right here with the negative 1 to dx will cause problems because if x is an integer that is even, this negative 2 to dx will be positive, but if x is an odd value, it will actually be negative. And so you get this flip-flop back and forth between positive and negative values, which is why we want to stipulate that b is positive. And we also want to stipulate that b cannot equal 1 because 1 to any power is just 1. Alright. And with that, we define the inverse trig, or not inverse trig, but the inverse law, or we define the inverse exponential function to be the logarithm. So if y is equal to b to the x, then the inverse function for the exponential is going to be log base b of y is equal to x. So these are interchangeable ways of rewriting the same quantities. It just depends if you want to think in terms of exponential or logarithm. And we still have the same stipulations that b has to be positive and not equal to 1. We said that the common logarithm is log base 10. So log base 10 should be written as log. In fact, this right here, log base 10, that is bad notation. So that's the common log. It's just a log without any base being written right here. And we talked about the natural log. That we said was log base e, which was Euler's number. And we want to think of that as ln, natural log. This would be bad notation again. Now, we've saw two applications of exponentials during our investigation. We said that the amount, well, we should say for compound interest, the amount is equal to principal 1 plus r over n to the nt. I don't know why I put that equal somewhere. That should be multiplied by. So this is the compound interest formula. And A is going to be our amount of money. P is the initial investment amount. A better word for that is principal. So principal. Actually, I think that needs to be an AL. Let's see here. Yep, AL. So that's the principal. R is our interest rate. That's a terrible R. Let's fix that. That look more like a D. R, interest rate. I don't know what I was spelling. Interest rate. And N is the number of times interest is calculated in a year. Another word used instead of calculated is compounded. Compounded per year. And we said that this would, if you were told that interest was compounded like semi-annually, then n would equal 2. Quarterly, then n would equal 4. We made a nice table with all that information already. So we also talked about the continuously compound interest formula. Continuously compounded interest. So that means every moment of every day over the entire year, interest is being calculated. So this was the amount is equal to your principal times Euler's number, RT. And what was Euler's number? In case you forgot, we hit second and then the division sign, E is approximately 2.71828, so on. It is a transcendental number like pi, which means it has an infinite number of decimals that cannot be expressed as a fraction. So our A, P, and R, those are all the same quantities. I suppose up here I should mention what T was. T was just time. Time in years. Alright, so A, P, R, and T are all the same, so it's now all the stuff here in the middle, the 1 plus R over N, it plus this N out here in the exponent, all that got condensed into our Euler's number, E here. And if you want to revisit, we do have that video called Discovering E that shows how we came across Euler's number using the compound interest formula. Alright, so then after we looked at these examples, we looked at logarithms again. We had these properties. So we said that if you have log base A of 1, that was equal to 0. Log base A of A was equal to 1. Now these are both just derivatives of this general fact here that log base A of A to the x is this x, and A to the log base A of x is also equal to x. So these two properties here on the right just follow from the fact that exponentials and logarithms are inverses of each other. We also had our 3 laws of logs, where if we had log of A to the C, that was equal to C times log of A. Doesn't matter what base. No, that's a terrible looking C. So that looks more like a C. If we have two quantities multiplied inside a log, we can turn it into a sum of logs. So log of A times B is equal to log of A plus log of B. And similarly, if we have log of A divided by B, we turn that into subtraction, where you have log of A minus log of B. And then we looked at solving exponential and logarithm functions in our basic strategy. So basic strategy for solving our equations were 1, isolate, yeah, we'll just write it out. So isolate the exponential or logarithm. 2, so we'll break this up into 2 steps. So if you have a exponential, you would use log it. And if you had a log, you would exponentiate. And then once you've done that, you would just perform your algebra and solve for x. And you would have to use your properties. So there are two properties we relied heavily on for our basic strategy in solving is these two right here. When you had an exponential, we would log it, and that would just give out the x. Similarly, when we had a log, we would exponentiate, so we can get whatever was inside that log. So that was our basic strategy. And then we looked at applications. So we had the doubling time method or doubling time model for exponential growth, and that was, let's say, population is equal to the initial population times 2 over to the t over d. So p was our population at time t. P naught is equal to the initial population. We usually talk about this in terms of bacteria, but it could be other things. Could even be money, theoretically. And D was our doubling time. And before I continue on with those, I do want to mention the change of base formula. Something I forgot to mention, I should have mentioned up here, change base formula. If you have log base b of x, you could change that into any base using the following ratio: log base a of x over log base a of b. So pretty much what was originally inside a log would go inside the numerator, and the old base goes inside the log of the denominator. And we proved this using our laws of logs. Coming back now to, we had doubling time. We also had relative growth rate. So the relative growth rate looked very similar. P is equal to P naught, but we now had an e to the RT. Where the difference is R is now our relative growth rate. And we had the relationship between R and D, which I forgot to put on my review. So let's go ahead and look that up real quick so that you have that, because that is important. So when we look at the exponential model for doubling time, it is this is strictly limited in terms of interpreting our population in terms of how long does it take for it to double. That's why it's called doubling time. Whereas when we look at this equation here, when we have an e to the RT, R is just the rate of growth, and then is reinterpreting this growth not in terms of how often does our population double, but just for continuously for every moment. So it's two different ways of interpreting the same phenomenon, and you can use either. And the relationship between doubling time and R is R will equal natural log of 2 over our doubling time. Alright. And then we looked at radioactive decay, and it's literally going to be the same equation again. So notice that relative growth rate, continuously compound interest, and radioactive decay is just three ways of reinterpreting the exact same equation. So radioactive decay, you have your mass is equal to your initial mass, e to negative RT. Same equation. In fact, the relationship between these two is even more similar. Like, I did not have to write that negative there. I could have just stipulated that like r had to be positive here. If r here was positive, here would be negative. Because we could think of whenever r is positive, then you're going to get growth, but when it's negative, you're going to get the decay. But instead of thinking of a negative rate, we usually want like think about it in terms of positive rate. So that is radioactive decay. We also talked about something called half-life. Now, half-life was how long it took for a quantity to have itself. So like different radioactive substances have different half-lives. Radium isotope 226 had a half-life of 1600 years, for example. So we had this relationship between half-life and our rate r, and it will also look very similar. So our radioactive decay rate r is going to equal natural log of 2 over h, where h is our half-life. So that's the relationship. We talked about all of that. We also talked about Newton's law of cooling. So Newton's law of cooling. So if we have a temperature, capital T, if we want to know the temperature of some object that's hot and cooling down, we can think of it as the temperature of the surrounding environment, T subscript S, plus our T naught, e to the negative k t. So I don't know what I was thinking there, but I'm not making a k. There's our, that's the k. We want to think of that k as a net exponent. So Ts was the temperature of the surrounding environment. T naught was a little trickier because we want to say it's the initial temperature, but it is the initial temperature of the object. So if you had a nice hot turkey, it would be the initial temp of your turkey, or whatever it is, but you have to subtract T subscript S from it, so that's a little tricky. So if your turkey was 200 degrees, T naught is not 200, but whatever your room temp, whatever your 200 minus your room temperature. So that's important clarification. And K, this varied depending on what the type of object is, whether it's soda or your turkey, and we're just going to say it's just a constant, okay? But it will dictate, what it will do is dictate how quickly your object is cooling. So like the can of soda will cool at a different rate than the turkey versus, say, a human body, like if you, like what we had for the problem with the murder in it. Okay, so K here will depend on just what kind of object it is. And then after Newton's law of cooling, we looked at applications of logarithms, right? We looked at the pH scale, for example. So pH scale said that the pH is equal to negative log of the concentration of hydrogen ions. I think that's fairly straightforward. And we have the decibel scale. So the decibel scale said, I think I used a D. I don't remember. We'll just say it was. So it was 10 log of I over I naught. So we used the units dB for decibel, dB for decibel. And the decibel, the loudness of a sound, is equal to 10 times the intensity of that, or 10 times the log of the intensity over a reference intensity. Our reference intensity was the threshold of human hearing, which was 10 to the negative 12 watts per meter squared. And then we looked at the Richter scale, measuring magnitudes of earthquakes. So Richter scale said that our magnitude is equal to log of I over I naught, where I naught is equal to 10 to the negative 4. And then we had the moment magnitude scale. Alright, and the moment magnitude scale said that our magnitude is equal to 2/3 log of I over I naught. It's literally like the same equation for all three of these here. But in this case, our reference intensity is 10 to the 16. Alright. And that concludes our summary. So that is what we did for like 16 videos. Well, 15 videos, and this makes 16. That is everything we did in a nutshell, except for one more important detail that I'm thinking about it. We need to talk about the graphs, right? So when we think about a exponential function, y equals b to dx, it has a domain of all real numbers. We can express it a couple different ways. We can use this fancy R for all real numbers. The range, however, is going to be from 0 to infinity, but we don't include 0 because as we'll see in the graph in a moment, that the line y equals 0 is a asymptote. And then if we have our function y equals log of x, log base b of x, our domain is going to be from 0 to infinity, and our range will be all real numbers. So we can note the relationship here. The range of the exponential becomes domain. Right. Now let's go ahead and look at the graphs. So let's see here. Here is lovely Desmos. Y equals, how about, we'll just use 5 to the x as an example. So we can see our horizontal asymptote. What's happening again is as the x values become negative, what you have is like 1 over 5 to the x. So 1 divided by 5 to the x, which means our values get really small really quickly. But that quantity can never reach 0, so we get our asymptote. And we can note that as long as we have a exponential of y equals some number to a power, that they will all share this 0.01. We have y equals log base 5 of x, on the other hand. We can see that our asymptote is now a vertical asymptote at x equals 0. And we have this 0.10 that all functions like this log base some positive value other than 1 of x is equal to. So there we are. Here's our two graphs. Here's our domain and range. Alright, thank you for watching this video. If you have been enjoying our content, please consider subscribing. Um, what is up next for Math with Haas is trigonometry, which is very exciting, and we will be spending a lot of time on that. Alright, and it will probably, trig is usually about 3 chapters in a pre-cal textbook, whereas this is just one, so we might hit many videos. I don't know. If it took 15 for this topic, we'd probably hit 40 to 50. There's a lot of material we can cover. But maybe I'm just being optimistic. We will find out. Either way, please subscribe, support us on Patreon. Thank you for viewing and joining our math party, and I will see you next time.